Here are the notes for the third and final section of Unit 5, and the topic is impulse. So let's begin by looking at Newton's second law, which says that a net force, I'll add net here, produces an acceleration. Now, if we replace acceleration with its definition, remember that acceleration is change in velocity over change in time. So if we substitute that in for A, we have force equals mass times delta V over delta T. Then, if we were to multiply both sides of this equation by delta T, we get F delta T equals M delta V. And this is actually has a special name. It's called the impulse momentum theorem. And the left side of the equation is called impulse. So force times the change in time that the force is applied is called impulse, and it's actually measured in Newton seconds. And it is equal to the change in momentum of the object. So here I've got the equation written again, and just a reminder that change in velocity is final minus initial. Also, the symbol for impulse is often a J. I is used for other things in physics, and the units are the kilogram meter per second or the Newton second. So let's look at an example here. Explain how the concept of impulse can improve technique in hitting a soccer ball, or kicking a soccer ball, or hitting a baseball. I have a video, or I had a video queued up. Oh yeah, in YouTube. Okay, let's watch.
Question. Which provides the greatest impulse, a bunt or a base hit? Why? In our first example, we have a slow-mo video of a base hit. And I want you to think about how long the bat was in contact with the ball. Our next video is a bunt. Again, think about how long the bat is in contact with the ball. For comparison's sake, let's go back to another base hit example. Again, think about how long the bat is in contact with the ball. The ball had a much greater velocity during both base hit examples. Therefore, a base hit provides the greatest impulse and therefore the greatest change in momentum because the bat and the ball are in contact for the greater amount of time.
Okay. Oops. Switching all around here. So, in sports, often, we if we want to change the amount of speed that we give to a ball, there's a couple things we could do. We could apply a bigger force, and for that, your coach might send you to the weight room. But let's say you've maxed out the amount of force that you can apply. The next thing that you can do is you can apply that force for a longer period of time. And if you apply the force for a longer period of time, then you will have a greater change in momentum. Here's another example. I'm going to show you the demonstration first, and then we will do the problem. So here you're going to give your fire extinguisher to an astronaut, and the astronaut's going to use the fire extinguisher to move through space. So here the extinguisher has a force of 115 newtons, and Wally, the astronaut, has a mass of 70 kilograms, and we're going to activate and then deactivate this. You can see there's the astronaut holding a fire extinguisher. So we'll activate it, and you can see down in the lower left the amount of time. Now I'm going to shut it off. And the photo gate will tell me how long the astronaut went through the two photo gates. So let's do that again. This time I'm going to activate it for a shorter period of time. So when I activate the fire extinguisher for a shorter period of time, we have a smaller change in velocity. I'll do it again for a slightly longer period. So now it's going a little faster. So you can see the longer that we've activated the fire extinguisher, the longer the force is in effect, the greater the change in speed. Okay, so back to the notes. So let's suppose that this was our data. We would say that F delta T equals M delta V. The mass of the astronaut was 70. The change in velocity is basically equal to the final velocity, and the final velocity we saw from the astronaut going through the photo gates. The photo gates were 10 meters apart, and it was 3,518 milliseconds. That's 3.518 seconds. So this is our velocity. Our force was, let's see, 115 newtons, and the time that we exerted the force was 1,723 milliseconds, which is 1.723 seconds. So let's see what happens when we multiply this out. I'm getting out my calculator. On the left, I'm doing 115 times 1.723, and I get 198. And that's Newton seconds. That's the impulse. Let's see if it equals the change in momentum. 70 times 10 divided by 3.518. I get 199 kilogram meters per second. See, on the left I've got, oopsie, get my highlighter. On the left I've got Newton seconds, and on the right I've got kilogram meters per second. And those are equivalent amounts. Let's try another example. A 2,000 kilogram car traveling to the west is slowed down uniformly from 40 meters per second to 10 meters per second in 5 seconds. What constant force acted on the car during this time? How far did the car travel during the deceleration? Okay, so I'm going to draw the car. The car is traveling west, which is in our cardinal directions to the left. Let's see. The mass is 2,000 kilograms. We've got an initial velocity of 40. We've got a final velocity of 10. We've got a delta T of 5 seconds. And we'd like to know the force. So we've got F delta T equals M delta V, or you can write that as M final minus initial. Okay. F times 5 equals 2,000 times 10 minus 40. So then I'll solve this. And I get negative 12,000 newtons. What this means is that the force opposes the initial velocity, which makes sense. If it's slowing down, the force should be in the opposite direction as the initial velocity. In this system, actually, I set up that, let's see, that to the right was positive and to the left was negative. So I did it backwards. Okay, number 4. The graph above shows the force on an object of mass m as a function of time. For the time interval 0 to 4 seconds, the total change in momentum of the object is what? Okay, so let's take a look at this. This is a force versus time graph. The area of a force versus time graph would be equal to force times time, or change in force times change in time. And what we've just learned is that that value is impulse, and it's also equal to change in momentum. So if I were just looking at the first 2 seconds, I would calculate this area, which is 10 newtons times 2 seconds, or 20 Newton seconds. However, it's for the entire 4 seconds. And remember that momentum is a vector, and the next 2 seconds represents negative 20 Newton seconds. So these two values are going to cancel out, and we would have a change in momentum of 0 over the entire interval. So what does this mean? When we see a force versus time graph, the area equals the impulse, and it also equals the change in momentum. Sometimes you may see, or I've seen a lot of graphs from the College Board that are triangular in shape. So let's just do a little practice here. Let's say that that was the scenario, and they asked us to find the change in, actually, let's say that they asked us to find change in velocity if the mass of the object is 5 kilograms. Okay, so the first thing that I want to do is find the impulse, which is going to equal my change in momentum. And the impulse is going to be equal to the area, which is going to be 1/2 the base times the height of the triangle, which is 1/2 times 6 seconds is the base. There's my base. And then the height, in this case, would be 20. So my area is 60 Newton seconds, or 60 kilogram meters per second. And that's my change in momentum, or my m delta v as well. Again, the impulse momentum theorem says that impulse and change in momentum are equivalent. So if the impulse is 60 kilogram meters per second, and the mass is 5 kilograms, then I would divide to find delta v. So 60 divided by 5 would give me a delta v of 12 meters per second. All right, thanks as always for watching.